Meiri from the Technion, and Chen has been, hold on, there is, yeah, Rami, the link for the slides is here again.
They appear as Nir writes them. They are not prepared ahead of time, right?
Yes. Well, half of it. You'll see.
We'll see.
And so this is joint work with Chen Meiri, and Chen really has been the main driving force in this project. And many times I would, he would come to me with this great idea, and I would, think about it and explain to him that there's no way that everything he says is can't be true, and it's too good to be true, and he would just listen to me and then at the end say, but I have a proof. So this is how much of this project was advanced. And both Chen and I are group theorists, and this lecture is going to be about arithmetic groups. Okay, so groups that looks like G of O, where G is a semi-simple group scheme, and O is a ring of integers, or even a ring of S integers, if you want. Now, one of the things that is very prominent when you in this theory of arithmetic groups is that there is a big dichotomy between arithmetic groups of low rank, and when I say rank, I mean S rank, between low rank groups, meaning groups of rank 1, and groups of high rank. Okay, you see this in representation theory. There are some instances, but it doesn't take such a front seat role. So to begin with, I want to start with a provocative question. And is it true that every matrix, every n by n matrix with determinant 1 is a commutator? Okay, so you know that SLN, so if n is bigger than or equal to 3, if SLN Z is a perfect group. So every element is a product of commutators. But the question is, can you have them, can it be that every element is actually a commutator? Okay, and we don't know the answer for this. But few remarks. First of all, n equals 2, the answer is no. Not just because that SL2Z is not perfect. SL2, the commutator subgroup of SL2Z has index 6 inside SL2. Inside SL2Z, but more than this, it fails in the worst possible way. There are elements that are product of 2 commutators that are not a commutator. There are elements that are product of 5 commutators that are not product of 4 commutators, and so on. Okay, so this is one. So I don't think that every matrix is a commutator. I don't know the answer, but this is one of the places you start to see a big difference between low rank and high rank.
So for SL3,
for SL3 Z, I don't know the answer. No,
for 3 you don't know.
Right. For any n. Let me just, just say from the start, writing that this is a question about solving an equation. Okay, that's the question about solving an equation of the form x inverse y inverse xy equals g. Okay, you're asking whether this equation has a solution for every g. Nevertheless, we know something. So Dennis and Wasserstein in, I think, 35 years ago, 40 years ago, proved that every matrix is a product of 6 commutators. Okay? So it's not, so maybe it's not a commutator, but it's a product of 6 commutators, which again stands in contrast to what happens for SL2.
Nir, what happens for SL2 again?
For SL2 is almost a free group.
Mm-hmm.
Okay, so let's talk about free groups. In free groups, there are elements, the element, take the commutator of xy and the commutator of x squared and y squared.
Mm-hmm.
This element is not a commutator. It's a product of 2 commutators, but it's not a commutator itself.
Mm-hmm.
Okay, and you can, in general, construct an element which is a product of 1,000 commutators.
I see.
But not a product of 999 commutators.
I see.
Okay.
And it is true that every element is a product of some number of commutators.
Right, because because the derived subgroup of SLN is SLNZ is SLNZ. Okay, because it contains, for example, all elementary matrices, and SLNZ is generated by elementary matrices.
Of course.
Okay. Now, when you have such a theorem, you can start asking, you know, what's so important about commutators? I mean, commutators are important, but why restrict yourself to commutators? You can ask about, is every element a product of 4 squares? Or every element, is it a product of 9 cubes? Right? And more general, you can start asking about some Waring type problems, some group theoretic Waring type problems. Okay. And the general setting for such question is the following. So a word, so let me just define, a word is an element of a free group. Okay. Now, if you have a word, so a word in k variables, x1 up to xk, and you have a k tuple of elements in a group, g1 up to gk, you can substitute gi instead of xi in the word and get a big product in the group, and you can evaluate it. So you get an element in the group. And you look at the collection of all such elements. So a word, so think about an example of a word would be the commutators, right? X minus 1, y minus 1, xy. Okay, that's an example of a word. And the set of word values is going to be all possible substitutions of elements in G into the word. Okay, so in the case of a commutator, what you get is the set of commutators. And finally, the width of G, of W in G, is the infimum, so a minimum, no, infimum, because it can be infinite, of K, such that if I take this set and multiply it by itself K times, by this I mean elements that are product of K elements, each one of them is in WG. What you get is the group generated by W of G. Okay, so the right-hand side is everything that can be written as a product of some number of commutators. Say a word is a commutator. And the left hand, and the question is, if it can be written as a product of some number of commutators, is there a bound on this number? Okay, and we say if there is a bound, we say that this bound is the width. And
it's not the same K, right?
Say it again?
It's not the same K as before.
No, it's not the same K. No, you're right. L. Thank you. There's no connection between K and the width in general. And so, and if there is no such a number, then the width is infinite. Okay. So, for example, what I said about the free group is that the width of commutator in the free group is infinite. Okay. And the Waring type problem okay, for example, what is the width of the word x squared? Okay, so it turns out that in SLN n bigger than or equal to 3, the width of every word is finite. Okay. Moreover, we know the following: if you take any word, the width of it in SLN is bounded by a function of n. Okay, it means that it's not 6, but for SL3 maybe it is 80, and not just every element is a product of 80 commutators, but every element is a product of 80 squares and 80 cubes and 80 1000s powers, and so on. In this aspect, the Waring problem behaves better in SLN than it does in Z. Another thing that we can show is that the width is bounded by some function of the word. Okay, just like in Dennis and Wasserstein, this 6 was good for all n. We can show this is true for every word. Okay, squares, angle words, whatever. Favorite word. And you can do better. It's not bounded by a common bound, by universal bound, but we understand what happens there. Okay, so these two theorems are actually corollaries of what I'm going to write now. What we actually proved is that the width of a word in SLN Z is bounded by some universal constant independent of everything, plus the width of this word in the post-finite completion of SLN. Okay, now the post-finite completion of SLN, we know it. It's just a product of all SLN ZP. Okay, so this number is the maximum of the width of W in SLN ZP. And that's a much easier question to deal with because, two things. First of all, that's a post-finite, it's a post-P group, virtually post-P group. You just need to understand what happens in each stage. Okay, and better than that, it's a periodic Lie group. There are methods that you can apply from periodic analysis to do this. Okay, so for example, the open mapping theorem is very useful in these type of questions. If you know that you do some derivative computation, and then you get that your word value is, if your word is good enough, or if you take enough product, you know that your word is the word, the set of word maps is at least open. Okay, and so just one remark, this width is clearly bigger than or equal to the width of W in the post-finite completion. Because if you have a surjection, from G to H, then the width in G is bounded below by the width in H. Okay. So it's true for. Sorry.
Can I ask a question? So
yes.
Isn't it true that the width for SLNZP is 3, like for all periodic groups? I'm confused. Like, what do you mean by
depending on the
word?
No, it depends on the word.
You mean by with W SLNZP, you mean
if you fix W and take P to infinity, for P large enough, then the width is 3. Okay. This is what plays a role. This is why I said that 1 and 2 do not imply a fixed constant. There is this problem. Okay. Okay, so you can view this as some kind of a local to global.
What are you actually using about SLN?
In this proof, I'm using quite a lot. I'm using for this, I'm using bounded generation. I use the fact that SLN Z, every element, I know that every element is a product of elementary matrices, but I'm using the fact that every element is a product of bounded number of elementary matrices.
Okay, thank you.
Did I answer? Okay. That's a very non-trivial claim. And that is part of the problem to generalize this theorem to other arithmetic groups, because we don't know this claim, okay? We don't know a similar claim. We know this for Chevrolet groups, but other than that, we just don't know. We don't know it's true, and in some case, we don't even have a guess what should replace it. For example, if your arithmetic group is anisotropic, so it's a co-compact lattice somewhere, it doesn't have any unipotent elements. Okay.
So, do you know it for a group with higher rank over the algebraic closure?
No, we know this theorem. No, we don't know this.
Because you also don't know finite bounded generations there.
Right. We do know it for Chevrolet groups. Okay, I'm just saying SLN because there's no new math that comes into the game. But there will be something new, some new idea if you want to extend it to other lattices. So this might be, this result might cause you to conjecture that the width of a word in gamma is bounded by some constant plus the width of W in the profinite completion of gamma, but it's false, this conjecture. That's a fake conjecture, okay? And the reason it's false is that you have, so you have groups such as, let's look at SO. SO of the following: x squared plus y squared minus square root of 2z squared minus square root of 2w squared. So SO of this quadratic form, okay, which sits inside SO22 R, and it does have high rank, okay. But if you apply Galois automorphism, it also sits in a compact group, SO4 R. And it turns out that for compact Lie groups, there are words that take everything to a very small neighborhood of 0. Take all the group to a very small neighborhood of 0. And it doesn't happen for the profinite completion. These words don't send the profinite completion. In fact, the width of these words is 3, or maybe 4, something like this. Okay, so there is another obstruction to the width, another bound to the width coming from compact factors. Okay, but I think that's it. I think that is the only obstruction, and we conjecture that the bound is really the constant plus the width of W in the Bohr compactification of gamma. Let me explain. The Bohr compactification of gamma is the limit, just like the profinite completion is the gate to finite groups. It's the limit of all finite groups that you surject on. The Bohr compactification is the limit, the inverse limit of all compact groups, compact Lie groups, together with a dense homomorphism. So G such that rho, so G compact, and rho from gamma to G has dense image. Okay, so and you're not adding too much. Okay, so if you take a group like it's easier to work with simply connected. So if you take a spin group of F of some quadratic form, and you ask yourself, what is the Bohr compactification of it? Let's say O. Okay, so the Bohr compactification, let's start. The Bohr compactification of SLNZ, n bigger than or equal to 3, is just the profinite completion. Okay, but if you take other lattices, it need not be, but you only get the obvious things. So the Bohr compactification would be the profinite completion times, or maybe has finite index in. Okay, this equality should be taken with a grain of salt. It's subgroup of finite index. Times the product over all valuations, infinite valuations, such that f of v is definite of the corresponding spin fr. So this is just spin n r, the compact group. Okay, so Jonathan, so hello. Sorry. Pleasures of working at home. Okay, so you just need to understand finite groups and Lie groups in order to understand, according to this conjecture. I don't know if it's true. In order to understand the width of words in arithmetic groups. Okay, so now I want to zoom out. Okay, to a much more zoom out until I can barely see question and ask more generally, which equations are solvable in gamma? How do you, is there an algorithm, for example, that tells you if your equation is solvable? Is there an algorithm to, if it's solvable, to give you all the solutions? Okay, and even more generally, okay, you would like to know which first order statements hold in gamma. Okay, so the solvability of equations. So for example, to say that every element is a commutator is a first order statement, right? It says that for every G, there exists X and Y such that something happens. But it's a very special first order statement. It talks about, it's of complexity 2, right? There is for every and there exists. Okay, but you can ask this question more generally. And here you see a very big divide, very big dichotomy between low rank and high rank. Okay, so let me start. So the rank 1 group, so I'm going to talk about free group and surface groups mostly. Some of them are true for for other rank 1 groups, but I don't want to get into it. So first of all, there is an algorithm for solving equations. Okay, this question of whether you have a system of equations in the free group, can you solve it? That's an algorithmic question. It's decidable. And moreover, there is an algorithm to construct all solutions. So this is work of Makanin and Rasborov. Okay, it's basically what number theorists call reduction. So you start. So it's an algorithm to simplify equations. Okay, just some non-commutative version of Gauss elimination until you simplify your equation more and more until you get to some standard form. Okay. And then Tzvi Sela took this algorithm and made a geometric theory out of it that allowed him to say much more about the theory, the first order statements that are true in free group or surface group or hyperbolic groups more generally. And what he showed is that there are very few definable sets. In many meanings, okay, so if you know the theory is stable. But let me give you a theorem of Myasnikov and Kovich. Just to exemplify what's happening is that every definable subgroup, so every proper definable subgroup is cyclic. Okay? So a free group on 2 generators contains, as a finite index subgroup, a free group on 5 generators, but it's not definable. Okay? Even the finite index subgroups are not definable. And finally, and again, I think this is Tzvi's motivation for this work. The first order statements don't tell you much about the group. Okay? So what Tzvi actually showed is that the free group on 2 generators and the free group on 3 generators and the free group on 4 generators and so on all satisfy the same statements. Okay? And it's also true for all surface groups, non-commutative surface groups. They all satisfy exactly the same first order statements. All equations, all types of equations have solutions in one, if and only if they have solution in other, and so on. Okay. That was a famous conjecture of Tarski. Now, it turns out in the high rank case, the exact opposite happens on all of them. Okay, so I wrote here high rank star because we don't know this for all high rank groups. We know this for many high rank groups and conjecture that it's true for all. I'll tell you what we know in a minute. But let me just write. So not only does not exist algorithm, the solvability of a system of equation is undecidable. Okay, and in the high rank case, there are tons of definable sets. Okay, there are definable sets in industrial quantities. Okay, so for example, every finitely generated subgroup is definable in such a lattice. And finally, which I think is the most interesting phenomenon here, is that you can distinguish high rank lattices, but better than that, you can isolate a high rank group from all other, not high rank group, from all other finitely generated groups. Okay, and you can do this with a single statement. Okay, so you can axiomatize your group. There is a first order statement such that every finitely generated group that satisfies it is SL5 Z. Okay. Any question?
So Nir, maybe you mentioned this, but like what causes this big difference between SL2 and SLN for larger n? Like just being almost a free group, or?
They are different. I mean, there is this dichotomy, and it's real. It happens all over the board. I can talk about the proof, right? What happens in rank 1 that doesn't happen in high rank, or what happens in high rank that doesn't happen in rank 1. But there is no, I don't have any simple explanation or any procedure. Yeah, I don't know how to answer this without going into the proof. Okay. So let me do this. I'll go into the proof, okay? And the key idea in doing this, and the thing that implies all of those properties of high rank groups, is this notion of, this logical notion of bi-interpretability. Now, so this is something quite amazing that I learned during this, during the work on this project. In logic, so we are all used to equivalence relations between mathematical structures that are not isomorphisms. Okay, so so in algebraic geometry there is derived equivalence of varieties, and in commutative in rings there is this notion of Morita equivalence of rings, and I don't know, in differential geometry there is this notion of two manifolds that are isospectral. They have the same spectrum of Laplacian, and so on. But they're all talking about equivalence between the structures in the same category, more or less. Now, logic is much more general, right? Logic spans the whole of mathematics, and it was amazing to me to find out that there is a notion, okay? There is a notion, non-trivial notion of equivalence that allows you to compare two structures in completely different mathematical theories. So think about it, if you don't know this already. What kind of non-trivial relation can you have between a graph, a combinatorial graph on one hand, and the differential equation on the other hand? What kind of equivalence class that will happen for some graphs versus differential equation and will not happen for another? Okay, and it turns out that there is such a thing, and that's the notion of bi-interpretation. So by interpretation is maybe to this audience, the best way to introduce it as a kind of Morita equivalence. So every mathematical structure, every language in mathematical structure, so be it groups, graphs, rings, and so on, there is a notion of definable set. I said it before, but let me just remind you, a definable set is something of this form. You take your structure and you take a formula. A formula is a first order statement, okay, but with 3 variables, okay? And then, so if it has 3 variables, it doesn't have a truth value. It depends on the variable. So you go and you plug in every value possible. And for some of them, it's true, and for some of them, it's false, the statement. And then you take only those where the value is true. Okay, so for example, if my formula on the variable g is there exist x and y such that the commutator of x and y is equal to g, then the definable set corresponding to it is just a set of all squares. Sorry, a set of all commutators. Okay, so there are lots of them. There are lots of definable sets, and in fact they form a category. Okay, there is a notion of definable function between 2 definable sets, and the definable function is an actual function whose graph is definable. Okay. So you have this category of definable sets, and you have another category of definable sets. So definable set corresponding to some graph, and definable set corresponding to some differential module, something that corresponds to a differential equation. And now these 2 definable sets, so 2 categories can be equivalent or not, and that's by interpretability. Okay, so it's roughly equivalence of categories between the categories of definable sets. Okay, once you have this, equivalence, just like in Morita equivalence, in all other Morita, all other equivalences, you can pull information from one structure to another. And in our case, what we do is pull information from Z, from the integers, okay? And for example, the insolvability, the undecidability of equations comes from Hilbert's 14th problem. I forgot, the one that says that the Fountain equations, solvability of the Fountain equations is unsolvable. Okay? The fact that there are many definable sets come from Gödel, from Gödel's work on the fact that every recursively enumerable set in the integers is definable. And the fact that you can isolate a group, so you can axiomatize a group, comes from another theorem of Gödel. Actually, it's not trivial to deduce it. It's a theorem of Khalif. So one of the inputs that comes into this is the theorem of Khalif. But Gödel proved before that you can axiomatize Z among all finitely generated rings. Okay, there is a single first order statement that if a finitely generated ring satisfies, it's isomorphic to Z. And Khalif imitates this idea to show this for every structure that's bi-interpretable with Z. So here's the our theorem. Okay, that if gamma is a high rank group and it's centerless, and we don't know this for all high rank groups, but this we know for most of them. So if gamma is isotropic, okay, meaning it comes from an algebraic group of Q rank bigger than or equal to 1, or if you like geometry, it is not a co-compact lattice. Okay, or in order to deal, we can deal with some co-compact lattices, but only of orthogonal type. Okay, so if gamma is a lattice of orthogonal type, in dimension big enough, this is really well, I don't want to say anything. Then gamma is bi-interpretable with Z. Okay. Now, let me just say, so it looks too abstract, I bet, this bi-interpretability as an equivalence of categories, but what does it mean, an equivalence of categories? So you have here the definable sets over gamma, okay, that you can use that you can define using group operations. And you have here the definable sets over Z. And these categories are equivalent. So it means that there is a functor. There are two-way functors, but in particular, there is a functor from definable sets over Z to definable sets over gamma. Okay. Now,
Nir, I apologize. Maybe you said and I missed. I always thought of definable sets as subsets of something.
Yes.
How is it a category?
So its objects are subsets of, so its objects are subsets of some power of gamma.
Of some power of gamma.
Of some power of gamma, yes.
Mm-hmm.
Its morphisms, and its morphisms are also some power of gamma, but they are morphisms. Okay. Now, which reminds me that I forgot to say something. This roughly, okay, now it really bites me in the ass for not saying anything. When I say equivalence of categories, I need to decorate this. Okay, so these are monoidal categories. If you have two definable sets, their Cartesian product is a definable set, and I need this this equivalence of categories to be given by monoidal maps, monoidal functors. And moreover, it's not exactly true. These are categories of sets. Okay, and I really need this category, this equivalence of categories to be over sets. So technically, if you like this language, if you don't ignore it, doesn't matter for this lecture. But technically, you look at this category of definable set is a category over the category of sets. Okay, and this equivalence should be an equivalence in the slice category, in the over category, or in the over two category of the over the category of sets. Okay, but it doesn't matter. Let me just tell you more precisely what needs to be done in order to construct such an equivalence. So the first thing that you want to do is to show that there is a functor from definable sets of Z to definable sets over gamma. And in particular, it should take Z somewhere to some definable set, X. And it should take the product, which is a binary operation. It's a function from Z cross Z to Z. It should map it to some product, some binary operation on X, and similarly, addition should be some other binary operation. Okay, and because of this structure, what you get is that you get that this definable set, together with its direct sum and co-product, is a ring. And it's a ring isomorphic to Z. That's one of the requirements here. Okay, and so, and I think that that's it. Okay, because all this category is generated by this object and these two morphisms. Every definable set you can get as some diagram using Z and or powers of Z and these two morphisms. So in order to give so again, in order to give a functor, what you should just do is to find a definable set and two binary definable operations that's isomorphic to Z. Okay, so I like to think about it as emulation. Like I have a Macintosh here, but if I want to run but I can run an emulator for Windows machine inside my computer. Okay, and the next thing that you want to do is to find a functor in the other direction. So you want to emulate gamma inside of Z. This is, in our case, it's easier, right? Gamma is some group of matrices. Clearly, you can emulate it, but that's not enough. Okay, that's not enough. Because two-way functors are not necessarily equivalents. What we need is that there is a natural transformation, and this usually is the hardest part. Okay, not to prove that there is a natural transformation. Okay, let me say what do I mean. So, not a natural transformation between these functors, a natural transformation between the composition and the identity. Okay. At the end, what happens is that you emulate gamma inside the copy of Z that you emulate inside gamma. So you emulate gamma inside gamma. Okay. And you want to show that this emulation is definable. And it's not at all clear. So let me give you just an example. You can emulate the complex numbers inside themselves, okay, by choosing an isomorphism between C and itself. Okay, you can choose the identity, and this will be definable, but you can choose any Galois automorphism of C, and that will not be a definable map. Okay, so you need to choose your functors very carefully. Okay. Nevertheless, I'm not going into the proof, but what I do want to point out, and I think this is, I know this was very surprising to us, that when we proved this theorem, we had this condition of centerless, and we thought it's we left it to the end and said, okay, let's write it with this condition. Then at the end, we'll just see how to omit it, because there is not a lot of difference. Centers in these groups are finite. Okay. But it turns out that it is not that it's not the case. The removing this condition is very much related to solvability, to word width in groups. Okay. So let me just say, so you would think that if you take a group which is bi-interpretable with Z and take, this group times Z mod 2, then it would be bi-interpretable with Z. So easily see that it's bi-interpretable with Z. But it's not the case. It turns out that it's very much connected to words in your group G. Okay, and that's the theorem. That's the last theorem that I want to talk about. So if you have a finitely presented group that is bi-interpretable with Z, and you take a central extension and a finite central extension of where your kernel or your center has size D. Okay. then if you want to induce this by interpretation, okay, so delta is by interpretable to C if and only if the width of some word in gamma is finite. Okay. So in principle, there might be a way to answer width questions in groups using logic, using some equivalence of categories. If you can show that, so we know that P, S, L, N, Z. So we know that, let's say, P, S, O, F, Z, or O, whatever, is bi-interpretable with the integers. Okay, if you can show me that this, degree 2 extension, so the central extension by Z mod 2 is bi-interpretable with the integers, then that's equivalent to showing that the width of squares is finite. Okay, and now this is what I wanted to say. Thank you very much.
Questions, please.
Hi, I have 2 questions. So first of all, is it true? So you mentioned that like you can deduce Hilbert 10 for gamma from Hilbert 10, like from the original Hilbert 10. Is it something that you can deduce in the other direction? Like, is there something which is easier to prove on gamma that you can somehow deduce on the integers?
I mean, equations in gamma are right. No. Equations on. Sorry, I didn't understand the question. So equations of gamma are particular cases of equations in Z, right? You can rewrite any equation in gamma as a Diophantine equation. So that's the easy part.
Okay. Okay, I see what you mean. So it's.
So,
okay.
But maybe you asked something else.
No, okay. I think it's probably a bad question. Another question. So about something I didn't understand about the width of words. What happens if you take like a word which is, let's say, some power of SLN F3 or something?
What do you mean,
then,
a word which is a power of SLN?
Which is x to the power of the certain number of elements in SLN.
Mm-hmm.
So it does not have a width, finite width in SLN, right? In SL3 Z.
No, it does. It does. So if you look at this x to the n, okay. So it turns out that this word, okay, doesn't matter. So if you look at this word and you look at this map from SLN cube to SLN, okay, this map has the derivative of this map is onto. Okay. Okay.
Yes.
So it's a dominant map. Okay. It means that if you, for every p that you plug in, okay, even z2, okay, the image is going to be open. Okay, and therefore it's going to have finite index. So so the image is going to be open, and then after, so let's call this function f of g3, okay, its volume is going to be bigger than epsilon.
Mhm.
Now, when you start multiplying, the volume each time gets at least epsilon higher. Right?
Can't you be inside like G1 ZP? Like
You can.
but then
But it stabilizes. Oh, okay. So maybe
okay. By width, you mean that you generate what you can generate. That's what you mean by
yes.
width?
Okay. Yes.
Okay. So now I understand.
So,
Okay.
right. So that was the equation.
Okay.
I don't ask it to be I don't ask it to do the impossible.
Okay. Thanks.
So, can I ask a question?
Yeah.
Can you go back to the previous slide for a moment?
This one?
Yes. So, you said that two things are equivalent. So, are there examples when they're both wrong?
Sure. Well, in the for groups that are bi-interpretable with Z.
So the gamma is bi-interpretable with Z, but when you take its central extension, so in this world of lattices, it stopped to be bi-interpretable with Z and stopped to have finite. No, but it has to have finite width. So if gamma is a lattice of high rank, I know we say we don't know for lattice.
We don't know.
But if it's like Chevalier group, then everything is okay. Yes.
If it's Chevalier group, then they both hold. Yes. I don't know of.
So also you know to prove it for Chevalier
lattice.
groups with non-trivial center.
Correct. So I know to do this by interpretation. Yes. Yes, but Chevalier groups have bounded generation, and it makes another proof much easier.
So for Chevalier groups,
I don't get. So I can prove both of the sides of this equivalence much easier than the equivalence. Well, it's not true, but I can prove both sides rather easily.
I see. And so you said by interpretation, there is one hard part there that after you find both of the interpretation, you have to find. So you have so SL2-3 that sits inside some large power of SL2-3 or SL3Z sits inside some large power of SL3Z, and you have to prove that this map is definable.
So this isomorphism, what you find is an isomorphic copy of
SL3Z
in a very large power, but you want this isomorphism to be definable.
And you have an example of not bi-interpretation, but of two-sided interpretation when this isomorphism is not definable?
Yes. So here's not with groups. But I'll give you...
not the example that you gave with C, but with like SS3Z. Is it? So did you prove that any two-sided interpretation is in fact bi-interpretation?
No, it's not true that I can do something similar. I can do something similar with a group, something like SL3 Z square root of 2. And I can construct a good by interpretation, but then apply Galois automorphism to it.
Mm-hmm.
But maybe I'll give you an example. I think it's a more interesting example. Okay. I say that Z, the two rings, Z and Z direct sum Z, are mutually interpretable. So there is an interpretation of Z inside Z direct sum Z, and there is an interpretation of Z direct sum Z inside Z, but they are not bi-interpretable. Okay. So let me give you so it's clearly you can interpret Z direct sum Z within Z. You can also interpret Z as you look at Z direct sum Z, and you multiply it by the element 1, 0. Okay, this is a ring clearly isomorphic. This is a subring of, let's call this R. Okay, the subring of R and it's isomorphic to Z.
What do you mean multiply? So you take the
ideal generated by this element,
but
1, 0.
It's an actual like copy of the x. It's the x-axis, yes.
Right. It's isomorphic to Z.
But now explain me why the x-axis is actually definable, because it's the image of this guy by multiplication.
Right. It's the collection of all elements that if you multiply them by 1, 0, they remain the same.
Okay.
Or you know,
it's both image and.
It's both image and yeah, well, whatever you want. Okay. But Z and Z plus Z are not bi-interpretable. And the reason that they're not is that everything that's bi-interpretable with Z satisfies that you can show this directly. If you are bi-interpretable with Z, then every recursively enumerable set is definable. Okay, because it's true in Z.
What is recursively enumerable set?
So,
okay.
If there is an algorithm that generates this set, then using your operations, then it is definable. Okay.
Yes.
And I claim that the diagonal inside R, inside Z direct sum Z, is not definable. Although it is recursively enumerable. Okay, and it's not definable. That's a general claim, but let me just convince you. I claim that every definable set in Z cross Z has to be some kind of
product
rectangle. There is no
the union of rectangles is probably also okay.
A finite union of rectangles is okay. And when I say rectangle, I mean definable set in Z times the definable set in Z. But the diagonal is not one of those.
Finite union of rectangles is
because there is nothing in your language where the second variable, the second coordinate can influence the first coordinate.
But just maybe even more naively, why this? Why those two interpretations are not are not
okay?
One good
Because great, because in the end, if you write it down,
because the graph is again some diagonal.
You need to figure out whether this map. So X, Y. You need to figure out two things. Why is this map definable? And it is definable. Okay, that's just product with 1, 0. But you also need this map to be definable. Okay. And this map is not definable. There is no way in which some information about the second coordinate can go to the first coordinate. Just not in there's nothing in your language that allows it.
Not definable. I see.
So again, I say, if you take the two interpretations that I told you about, and write down what does it mean that at the end, the self-interpretation is definable, you get to this function.
Why is so I'm sorry, Nir, why you cannot mix coordinates or add coordinates?
Because your operations do not allow you to do this.
What are my operations?
Your operations are addition, coordinate addition, and coordinate multiplication.
But just coordinate wise.
If you have several copies of R, then you can You can interchange the coordinates, but
No,
R
yes,
itself
but-
is one. Just a moment. So how you have 1, 0? Is it constant of your
No,
language?
it's a constant. You add it to the language. You allow, when I say definable sets, I allow constants.
And in your theorem?
Both, in all theorems that I'm talking.
So what does it mean? So all elements in SL
So,
and Z?
so an equation could be
So
you
all
know, the
elements in SL and Z are constants in your language, yes?
yes, yes.
Can I ask also another question, please?
Yes.
If you look at the Heisenberg group, the maximal unipotent of SL3Z, is it also the same business with this?
That's a very interesting example. So if you look at this group, the Heisenberg group, so it is in mutual interpretation with Z. So it interprets Z, and Z interprets it, of course. Okay, but it is not in bi-interpretation. Okay, but if you look at this group,
All right.
then it is in bi-interpretation. Okay, so this bi-interpretation business does not pass to finite index subgroups.
I'm sorry, if Heisenberg group can interpret Z and Z can, what do you mean can interpret? It means there is a functor embedding like this?
Yeah, for smart people, there is a functor embedding, but the claim is that you can emulate the ring Z.
I see.
Inside this group. Okay?
Mm-hmm.
Let me tell you how to emulate. Okay, so your definable set is this. Okay, and it's definable because it is the center of the group.
Mm-hmm.
Okay, and you want to emulate addition and multiplication. Addition is just given by usual product. Okay, multiplication is slightly more complicated. What you do,
you claim that multiplication is definable operation on the node?
I claim that multiplication is definable operation on the nodes. So this function takes this pair to 1, 1, 1, AB is definable.
In group theory, yes, you only use.
In group theory, yes. So it's not so easy, but what you do is the following. What you do is you start with this element. Let's call it capital A. Okay, and you look at the centralizer of A.
You allow constants.
I allow constants. So this is this group. Okay. And once I have this element, I'm looking for an element in the centralizer centralizer of A. Okay, I'm looking for such elements. There are many, but if this holds, then X equals to 1, 1, 1, A something. Okay? Is this, I mean, something like this. If I have this element, I get a definable set of elements that look like this. So this is definable. Okay. So now if I take 1, 1, 1, A and 1, 1, 1, B, I can produce a set of elements of this form and a set of elements of this form. And when I take a commutator of an element here and an element here, I get the element, any commutator, okay? I get my product, okay? So if you wanted to define, you would say something like this. So you want to define X tensor Y equals Z, means there exists an element in the centralizer of X. There exists an element in the centralizer of Y, such that the commutator of G and H is Z.
And some other conditions.
No, that's a condition. The condition of the
centralizer.
Yes, just being in the centralizer forces you to be of this form. So no.
Intersection with
no, and there exists G such that G right is
some conditions
is X
and Z have to be equal to this.
Yes. Oh no, not the centralizer of X. The centralizer of this element.
And plus
it's something like that. Yes.
So
and then this definable set is a singleton, like it's one element. Which
it turns out that yes, all such element will give you, even though you define it as there exists and there might be lots of G and H, they all commute to the same thing.
And what happens, by the way, if you just do the AX plus B group?
What is AX plus B?
What R star R? So which group? Sorry.
Just the C is equal to 0. The 2, 1, sorry, the 2, 3 entry is 0. But obviously.
Wait. This one?
Sorry, no, this is
no. This is Z plus Z.
And as a group, Z plus Z is also not bi-interpretable with Z. Yes.
No.
With the group Z or with the ring Z? They're very different.
With the ring Z not, and with the group Z yes.
I don't think so. I don't think it'll be bi-interpretable with the group Z.
I mean, I guess my question is whether, the only proof I can conceive of is that you first work with unipotence. And then
no, so we don't. So the whole point of this project was to find new technology to deal with. What we do, we work indirectly. We work using the there's a lot of number theory there. We work. The first thing we show, and this requires a lot of. This requires some input and some improvements of things done on the congruence subgroup problem. The first thing that we show is that we can define the congruence subgroups. Okay, and then we need to find some. So you have your group gamma. Gamma is this spin group, this co-compact group. And so first of all, you figure out that gamma p are definable.
Gamma p are
Okay, and moreover, uniformly definable. So you can so the length of the defining formula doesn't depend on p, but maybe the constant does. Okay. And now you want to find a copy of z inside here. Okay. So what you do is you can define a torus. Okay, you can define a torus just by taking centralizer of a regular element inside.
torus. What do you mean?
The integer points of torus.
But it's just plus minus 1, no?
No. It's a spin group. You take a anisotropic torus.
Okay.
A big torus. Okay. T of O inside gamma. T of O is basically the ring of integers, the invertible element in some ring of integers or some variant of this. And then we use, and then we show that you can define finite sets in this T of O. Okay, and this we use a famous theorem of Siegel that says that this the only finitely many common divisors to both x and x minus 1. Okay. Sorry, not x and x minus 1. What do I want to say? Anyway, we use the theorem of Siegel, a number theoretic question about integers.
What do you mean define finite set? I mean, every finite set is obviously definable.
But uniformly, you can have one formula, so uniformly defined finite sets. So there is a formula in two variables such that if you plug an element in the torus in one of them and look at this definable set, it is always finite. So I'm saying something. There is a formula, phi xy, such that for every a, if you look at the collection of all y, such that phi a y holds, this is finite. Okay? And two, every finite set is obtained this way. Okay? Once you have this, you use a trick of Julia Robinson, and to show that you can actually define a copy of Z inside. It's a very indirect way. You don't construct it.
But if I just wanted to do it for SL3Z?
For SL3Z, it's much simpler. For SL3Z, you can define, you can use this one. It's the center of the centralizer of this element. So you take this is the center of the centralizer of this element. Okay? And to show that this map is definable, it's much easier. You take this element, you commute it to this element, you take this element, you commute it. You conjugate it, not commute it. You conjugate it to this element, and then you take the commutator. Okay, so again, I'm sorry. You have this element, and this element. So, and this element, okay? First map is so you claim that this map is definable. Okay, that's just conjugating the first element by a permutation matrix and the second element, and conjugating the second element by conjugation matrix. And then you take commutator, and you get this element. So, so finding an interpretation for SL3Z is quite easy. Finding mutual interpretations for SL3Z and Z is relatively easy. What's not so easy is to show that this map, so what is this map, what does it boil down to? It boils down to the following, to show that this function, the function that sends this matrix to this one, is definable. Okay, that's the non-trivial claim in the case of SL3Z.
So just on the practical level, the first mutual interpretation that you find a posteriori is in fact by interpretation? Or
What do you mean the first?
Like now you explain me some mutual interpretation.
Of SL3Z?
For SL3Z. This is
okay,
like
yeah,
the first thing that you made, or
that's
there
the
was
first
some other attempt?
No, that's
It was not mutual.
That's the first thing that you do, and it works, but it's not.
But it's hard to show it.
But it's not trivial. It uses this bounded generation result.
And also for higher rank, you say that the hard part is to, or one of the hard parts is to show that that mutual interpretation is actually by, but you don't tweak the mutual interpretation, or you do?
So so in the case of isotropic groups, in the case of isotropic groups, sorry, no, not even. In the case of groups with Q rank bigger than or equal to 2, it's quite easy to find, because you can embed SL3 inside. It's rather easy to find, or other groups. It's rather easy to find a mutual interpretation using these ideas. Okay, but it's not clear how to prove that. In the non-Chevalier case, it's not clear how to prove that this by interpretation works. It probably does, but it's not clear. In the in the compact case, in the uniform case, you don't even have a place to start. Okay, the only thing you have are tori.
Yeah, but you proved it for what kind of groups? For all lattices?
So we proved it. No, not for all high rank. We proved it for isotropic groups, but not Chevalier, isotropic. And we proved it for all quadratic, so lattices in orthogonal groups. Now, Probably with some work,
So
it
what
will
is
also.
isotopic?
Isotopic means, I don't know, depending on your taste, it means, so your group is G of OS, okay? And O is the ring of integers of some group K, and isotropic means that the rank, the K rank of G is bigger than or equal to 1. Okay. Equivalently, that's just to say that your group, your lattice gamma is uniform, is co-compact in its Lie group.
Okay, rank bigger.
Is not co-compact.
Sorry, it's not co-compact. Yes, yes.
So okay.
The hard part are the co-compact lattices. I know, maybe surprisingly.
And for them, you still believe it is true, at least something. Oh, you prove that it's true for some.
So we proved it for orthogonal groups. Now, what are the uniform lattices? So there are lattices in uniform groups. In orthogonal groups, there are lattices that are constructed using unitary form. Okay. And maybe something, in the symplectic groups. These are probably okay, and these are probably going to have the same proof. We didn't check. What we are clueless about are lattices that come from division algebras. Okay. Once you do this, that's it. You proved your theorem for all high rank lattices. That's the hard part is those lattices that come from division algebras, and it's not so surprising because even so we use results from the congruent subgroup problem, and this is exactly the case where we don't know the congruent subgroup problem.
Very nice.
Okay.
I mean, are they even known to be perfect?
How do we even know what?
I mean, these complicated groups that you mentioned, are they known to be perfect?
I mean, you can compute it, right? You know they're hold on. I don't even know that. I don't know. Any other question?
למה אנחנו מדברים באנגלית?
יש פה מישהו.
I think there is someone that does not speak Hebrew, but I'm not sure.
Okay, תודה רבה.
Okay, thank you very much.
Again.
Bye.
Nice. Avoid.